Well, thank you very much for having me at this conference in Seattle. It's the first time in this state. So famous for Mount St. Helens, and I'm sure other things as well. I've certainly come from a fair way, as you can see from this map here. But if you want to go a bit further, my name is actually a Hebrew name. It's the Hebrew word for Frenchman. So Sarfati means Frenchman in Hebrew. So I'm ethnically Jewish. I can tell Jewish and French jokes if I want, so I can get away with it. I'm also a chess master for what it's worth. I even play these little blindfold games like at this is a creation conference in Australia in 2004 where I played 12 games from memory. So I do a few little things in my spare time. But what I'm talking about here is the amazing issue of designed for life. And it's interesting to talk about what the evolutionists are saying. Look at this quote from Scott Todd. He said, even if all the data point to an intelligent designer, such a hypothesis is excluded from science because it's not naturalistic. Now you see the point, he's got a bias there. He is not going to accept a supernatural designer no matter what the facts say. It's a case of don't confuse it with the facts. But of course, as Frank said last time, science should be the search for true explanations, not naturalistic explanations. Because we can think about the things that we design. We're made in God's image. Part of that image would include creativity. We make things like the jet plane here. Now, how can you tell the jet plane's been designed? Well, one thing, it has oodles of correct components. But you realize that none of the components will fly. A jet plane is made 100% up of non-flying parts. So how do they become a flying machine? Well, the answer is they are organized correctly. Now, when you think of organization, you should think organizer. That's logical. This is real science, what we observe. Organization requires organizer. Now, evolutionists will, on the other hand, say that all you need for organization is a flow of energy through a system. Well, think about that. Bull in a china shop. What happens to that flow of energy through the china shop, okay? But hang on, if you harness the bull to a generator and use the generator to run a potter's wheel, then you could use the energy to make things. See the difference between harnessed energy by man-made machines, designed machines, and unharnessed energy, which is completely destructive. To give you another example, petrol or gasoline, you call it here, in your car fuel tank to the fuel line to the cylinder, where it ignites the chemical energy in the piston, in the cylinder pushes the piston, and that drives the car. Pour petrol on the outside of the car and light it. What's the difference, okay? Again, one is harnessed energy, one is unharnessed energy. And to give you yet another example of energy through a system, we'll think about this thing here. A frog in a blender, and you flick the switch, you're adding energy to the system, aren't you? And what happens? Oopsie, sorry. It's meant to, hang on, let me turn this thing on. Whoop. What is going? Okay, why is the sound not working? Don't worry about it then, okay. It's meant to have a sound here, but I think you get the idea. What you get is a frog smoothie. Okay, now why did the frog die here? It's because it got disorganized. Yeah. See, all the components are here. So why isn't the frog alive? Because the components are out of sync, aren't they? And if you left this going for millions of years, you think a frog's going to hop out of there again. It doesn't happen that way, does it? No matter what sort of energy you put into the system, no living thing is going to hop out of there again. And that's because every living thing is frightfully complicated. Even the simplest cell is frightfully complicated. If you want to think about a cell compared to a jumbo jet, for instance, a jumbo jet has far fewer component parts than any so-called simple cell. The idea of a simple cell is simplistic. There's no such thing as a simple cell. Think about a cell that has to make copies of itself. That's incredibly complicated. How do you make a machine that copies itself? We haven't got one of those. A photocopier makes copies of documents. It doesn't make copies of another photocopier, does it? You might have a factory that makes jet planes, but the factory doesn't make another factory. It only makes jet planes. But a cell makes copies of itself. See how much more complicated a cell is than anything that we can make. But think of other complex things. For instance, we're talking about flying things. Let's think about what natural flying things, like the feathers, for instance. See, feathers are incredibly well designed for flight, light and strong and aerodynamically good. Some evolutionists say they came from scales, but let's have a look at that. Look how different they are. I mean, the feather comes from a follicle like your hair. Feathers are more like hair than scales. The scales are just folds in the skin. And think about it, here's one evolutionist who basically gave up. He said at the morphological, which is the shape level, feathers are traditionally considered homologous with reptilian scales. However, in development, morphogenesis, gene structure, protein shape and sequence, filaments formation and structure, feathers are different, i.e. feathers are different in every way. But see, look at how they are. You see, look at the barbs here, and you've even got hooks and ridges, you see, which is why the feather can actually get into shape. You ruffle the feathers, you can still, the bird can preen them back into shape easily because of these natural hooks and barbs there. And that's how the feathers work. Now, the thing is, if reptiles evolved into birds, then where did the feathers come from? Another problem with reptiles into birds is the design of the lungs. I mean, our lungs are one marvelous enough. I mean, we went through it last session about how the air comes into these air sacs and then you've got the blood taking the oxygen out. But the thing is, the bird lung is a completely different sort of lung. You see, the bird lungs there's systems of air sacs here, but the bird lung itself, the systems of air sacs and valves push the air through in one direction through a whole lot of tubes. It's quite a different design. Instead of the bellows-like lung where air goes in and out in the same patches, air in out in the same, the bronchi and the trachea. Here, the parabronchi, the air is always going in one direction. And the blood is going in the opposite direction. It's called countercurrent exchange, and that's why bird lungs are so good even at high altitudes. They are very efficient at taking up oxygen. But then you have to ask, how could a reptile lung evolve into a bird lung? Well, see, look at what would have to happen. You'd have to have basically a hernia sort of thing. This is outgrowth. So the intermediate thing would have a hernia, a diaphragmatic hernia, and therefore they would be at a disadvantage. It would be a lousy sort of lung. So the thing is, natural selection would eliminate these so-called intermediate forms. And the thing is, if a reptile lung couldn't evolve into a bird lung, then a reptile couldn't have evolved into a bird. That's pretty logical. Now, also we've got plenty of other things which are just amazing in design. Now, one thing to think about is the issue of sonars. And guess what? We've got natural sonars. I'd say God made sonars before man thought of them. And in fact, the discovery of bat sonar roughly coincided with the development of man-made sonars. And when this was during the Second World War, the British scientists were worried about leaks and security and all that. They thought when the bat scientists were talking about sonar, they'd had a security breach. And they thought it was absurd that these little flying mammals that get in the belfries everywhere has this sophisticated sonar system they'd only just developed. But now we know very well bats have sonars, and in fact they say bat sonar is so much better than anything developed by human technology that little creatures seem to enjoy rubbing it in. And you even think man-made sonar can distinguish echoes 12 minutes of a second apart. That's pretty good, but the bats can go 2 to 3 million, so much closer together the pulses the bat sonar can distinguish. So bat sonars are better than man-made ones. And they even got other techniques, not just a straightforward matter of emitting a click and timing the echo. They've even got what they call sonar strobe groups, so they can target their prey and avoid all the other echoes from the clutter. There's clutter from all the other things that the echoes are bouncing off, but they can actually focus in on their prey. And then you think of what else the bat sonar can do. It's got volume control. Well, you think about this. Now, as you get closer to a sound source, it becomes louder. And that's one problem. How do the bat control this? In fact, you have to ask, why aren't bats deafened by their own clicks? Such sensitive ears, and you think their own clicks would deafen them. So how do they avoid this? They've got what you call time-varying gain control, like man-made sonars do. The bats thought of it first, which means God thought of it first, really. The bats didn't really think about it, did they? It's their maker who thought of it. So the thing is, what the bat does is it reduces its hearing sensitivity as it gets closer to the target, and it's because it has a certain muscle, the stapedius, as one of the ear bones is called the stapes or stirrups, and the thing is, it tightens it. You know, like in drums, if you tighten something, you can deaden the beat of the drum. The bat has something like that to deaden the eardrum. So it actually protects it from being deafened by its own sonar pulses, and it's pretty amazing there.